committee meeting of this conference last year in September, the local organizers came to the first meeting and they said that we must start each conference day at least at 10 or even later. And we didn't really understand that, but this time I can see that they had seriously right. Anyway, the gala evening yesterday was fantastic. I really hope that you enjoyed the dinner and the drinks. 2 announcements. Please, when you leave the conference venue, provide your or put down your bus passes. They have a limited validity. It's only valid at line number 20 and it lasts for, I don't know, Friday, no later than that. So please provide the bus passes because the cards are quite expensive. Thank you. The other announcement is that there's no lunch provided today, only for people who are staying for another meetings like General Assembly and some else. Okay, thank you very much. Thank you very much. So today's session is the last parallel session, users and applications, applications and mobility. We have 3 topics, 3 different topics, but they all about mobility and innovation in mobility. So our first speaker is Michael Lavov from University of Bremen. And you might remember that in Denmark, Lyngby, at the Eternal Networking Conference, we had a fantastically interesting presentation, plenary presentation on variable computing. So Mr. Lavov from the same group of researchers, and he will be giving us an update on the research what's going on in his group. So, please.
Good morning, ladies and gentlemen. Thank you for the kind introduction. My name is Michael Lavov. I'm from TZI, and I'm giving you a presentation on the project results of an IP which ended just last month. It was a 5 years IP. We were working on the idea how to empower mobile workers by variable computing. So the basic idea was to look for the next generation of computer users, people who are not computer users today, but will become the next generation of computer users. I hope I can make this with this machine. I'm really unfamiliar with it. So what we can state is that today every kind of information is available. We can have it here in this room. You have access to the internet. You can have access to your emails. Everything is fine. And you can store the information as often as you want at every stage. However, if you look at situations as they are indicated down here, so for example, during maintenance of an aircraft or during an emergency response or in a car, in the train, or during sports, you do not have the access as you are used to have it here in an office environment. What is the reason why? First thing is that we stick to the desktop paradigm. So we are focused to the machine. I can only talk to you if I look and want to look at you if I do not look at my PC. And if I want to get information from my PC, I can no longer communicate with you in the same way I'm used to without the machine. So the focus of the user is to the screen. It is stationary, and there is no interaction with the environment. So even if you want to have access here to the internet, you have to log in and do things manually. It is not done automatically. And if you leave the room, then you have to enter it again. So if you think of mobile computing as you do it today, and we are very familiar with using mobile phones or laptops or PDAs, we interact most of the time with the real world and interact only sometime with the mobile system. Because if we would interact with the mobile system during interacting with the real world, it would be very strange. There are some investigations done for people doing SMS or typing on the car navigation system during driving, and the performance is as bad or even worse than driving drunk and under drugs. So it requires attention to be interacting with the real world, and you cannot spend that interaction to the mobile device. The completely different approach is the approach of wearable computing, and here we assume that we have 100% interaction of the wearable system with the real world, and that the user has also 100% of its time for the interaction with the real world. And that the user is only interacting every now and then with the wearable device. However, it is done in an ambient way. So an example you all know is the use of the car navigation system. There you have the interaction with the real world using the GPS signals. And if you leave the road or miss an exit, then the system is recalculating automatically and indicating you the new way. And you have not to interact with the system. It is the only interaction you have is to input the information the system is outputting to you. So it is a very different way of interaction with the computer or with the device as in the desktop paradigm. And there are some other features which are very important. So for example, my mobile is now off because I'm talking to you, and such systems have to be always on because they are providing you with the information continuously, and therefore it has to be always on. And it is highly integrated into the clothing is highly integrated into your personal belongings, because otherwise you cannot wear it the whole day. So there are two things which are key and different to the desktop paradigm. The first thing is the way of interaction, and the second thing is the context detection. So at the beginning, we had the idea, okay, we take the computer apart and then make it mobile and let people use it like this. But I think it is not even possible to do it like this because we need a lot of energy for that. So it is not really wearable. If we see our application domains of wearable computing, then we have always primary tasks. Primary tasks that are tasks where we do something in the real world. Often there are manual tasks, and they require mobility. So we are not stick to one place, or only very rarely stick to one place. Usually the workplace is also a mobile one. And then there are secondary tasks, and the secondary tasks are supporting tasks, and they require the interaction with the wearable system. But the question is how to design this user interface. If you see that we always have the user and the system, and that we need some input modalities and some output modalities, then we have, for the input, a lot of challenges. So there are these device limitations. If we want to do things with our hands, we cannot use the hands to interact with the keyboard. And we also have, if we have to carry it the whole day, we have the limitations of the weight and the power consumption. We need novel user usage patterns. So there were keyboards developed for one-hand use, and there was also the idea to work with implicit input. So replacing input by the user by input coming from sensors. The example of the car navigation with the GPS is such an example. You could also input your new destination or your new position and let the system calculate those things. But the sensors are the sensor input is replacing the user input, and that makes it much more comfortable for the user. And the other thing is that it has to be used in the dual task scenario, so it must be possible to, for example, use it during driving or during maintaining a machine. There are special devices, where special devices developed, like this one-hand keyboard, also gesture input devices like gloves and wristbands, and also some special purpose devices. But we are still looking for something which is as universal as the mouse for the graphical user interface. So there's, even after the end of the project, still not the solution available on how to interact with the system. And the other thing is the output of the system. The head-mounted displays belong more or less essentially to the wearable computing application, but there are a lot of obstacles connected with a head-mounted display. They are disturbing. The cables are not liked by the users. They always have the feeling that they are wired. And so there's also an issue of, if you imagine I was standing here with a head-mounted display instead of standing in front of the laptop, you would feel a bit strange about me, because you think, okay, this is a techie guy or whatever. It is not appropriate for me in a presentation to use such a device. So the social acceptance, if you imagine the working environment in a factory, is even more different. And we had a lot of talks with physicians, for example, as one of our application scenarios was a hospital, and they said, okay, in the operation theater, no problem, I will wear it. But as soon as I talk to the patients, for example, during a ward round, it is impossible to wear such a device because people won't accept that. And the other thing is that it also requires some kind of new features to grab that there is information available which is essential. So we had a discussion within the project. Could it be that it is like watching TV all the time? And as soon as you see something which is interesting for you, then you look at it and then you take this information. And it might be that this is the way, but we need some kind of triggers to really make the people aware of essential information available. So if we talk about wearable computing, then there are also some other challenges. As you've seen in this introductory picture with a huge PC worn by the person, the size, the power consumption are issues, and the functionality of the system is also an issue. So if you use a system, then usually a one-purpose system is more appropriate than a many-purpose system, because the interaction with the system, due to the fact that the cognitive load is a problem for you if you want to do it in an ambient way, has to be somehow managed. The other thing is that any device requires power, so we are all able to be connected with the internet here in a wireless way, but we all need energy. And sometimes I think we are more energy junkies, that we always look, okay, where's the next plug to recharge my machine, and then that we have the worry about the interactivity with the network. And the other thing is also how to carry the whole stuff. In many user studies, we figured out that people don't like to be wired, that they don't like to have things put on their body or into their clothing, that what they really like to have is something that they can put on, as I can put on my jacket in the morning and everything is in. And I have not to care about if my phone is in or my pants are in. Now, the architecture we develop within the project consists of 5 components. There is a central component which gives us access to the other devices and gives us access to the network. There are the I/O devices. There are the sensors to replace input in an automatic way, and these sensors can be worn by the users, and it can be also sensors in the environment. And what is also essential, even if machines become more and more powerful, we cannot have everything on it. So we need access to external servers for content management and for powerful calculations, which cannot be done on a mobile device. Now, how did we solve this, this key issue of creating a variable user interface? So at the beginning, we had in the project about 42 partners, and about 20 of them were software developers. And the software developers were able to design very nicely graphical user interface because they were used to that. But they had no experience in different kinds of head-mounted displays, for example, or wrist-worn displays, and no idea about how to design an interface if it is a display to be used in daylight environment or in indoor environment, so different lighting conditions. Also no idea of how to use create an application which requires multimodal input and output. Because one of the ideas was, okay, we use speech, for example, speech input if we cannot use gestures, and we use gestures if we cannot use speech, and vice versa, and do it all automatically without bothering the user about that, so that you can just do something and interact with the system, and the system will understand that. And to overcome this problem that people did not know about how to create that, and that this requires a lot of special knowledge, we developed a toolkit for that to design user interfaces, where the application developer has only to design an abstract user model for the application, and the rest is then done by the toolkit from the drivers for the special devices as to the design, for example, if the head-mounted display, a monocular one, is on the right-hand side or the left-hand side, because it means really a difference in the displayed information. So this was one of the keys, and I want to show you, I hope that this is now working, let me see, a video on how this looks like. Let me see, I want to see it on my stick. Can you give me some assistance for this? Because I need the computer here, and this is Spanish. Yes, this is the one. Okay, and then now I want to show this video. Okay. Thank you. So this is a video on using a verbal computing system in an aircraft maintenance application. The user is wearing a vest. Within this vest, the computer is integrated, and he also the head-mounted display can be integrated if he is not wearing it. He's wearing a glove for interaction. And for logging in, he's using a RFID tag for the identification. And what you see on the right side there is what he sees on the head-mounted display. So he gets detailed instruction on what to do, and he uses the gestures to interact with the system. He uses RFID tags to identify the workpiece, and gets for this workpiece the related information. And then he does the operation, and he can use as well the gesture for the interaction as speech for the interaction. The one thing we found there is that annotation is a key point, because even in this simple example, there is a, let me see that this is, oops. Oh. This requires really some good finger. We realized that the workers got a lot of information which is not in the manual, and that this information has to be input somehow, and that it must be possible to give the user an annotation possibility, so that the system is creating knowledge all the time during the use of the system. We also developed a kind of a simulator to test different kinds of solutions for variable user interface designs. We call it the hot wire, to replace a manual task, and develop different forms for this device, just to make sure that the user is in the same positions as we observed them in the real environment, so that we could evaluate this kind of user interaction in a lab environment and see, look really for some reliable informations. The other thing is context detection, and we did some work on assembly training, where the workers needed some information for their tasks, and what we found out there is that we could detect quite well the motions of the workers if we have a lot of environmental sensors also available. And the point was that if we had that, then we could replace a lot of input, which usually the user had to do, for example, in this maintenance scenario, where the user, in fact, had to prompt any step he did. So it was more or less an automatic follow of working instructions, and always inputting what the user did. And here, it was different insofar as the user now got only the information if something went wrong. And so the user acceptance of such a solution was much higher. And this made us so confident that we decided, okay, we want to do a really challenging thing. We had the idea to go to the shop floor and look for quality assurance work steps in the Skoda factories that were partner in the project. And at the final quality gate, the assembly workers have to check about 90 different points on the car body. And they have to observe if there are any mistakes, if there are any failures, if there is anything not in quite order for replacing and redoing some work. And we try to the only thing we wanted to do is we wanted to put the user some wearable device on, and that the user then perform all the tasks, and we wanted to recognize what the user did, and if he did everything, so if it was really complete what he did. And and here I want to show you again a video. Oops, is it here? Oops, this is not working. That is, okay, it's not my machine. Sorry for this. Good, that is a problem if we use another computer. The codecs are not there. So what we did is we put the user's sensors in the blue code and some reflectors on the blue code, and we observed all the motions and tried to figure out what kind of action the person did. And we collected the signals, which were continuous signals, and did some analysis on the signals, first offline, and with the aim to do it online because we wanted to recognize the actions online. And what we found out is that we can recognize only if the person is only something wearing on the upper part of the body, only about 50% of the actions performed in a reliable mode. And you can see that in this image down there, there are in each line are the signals detected from the different sensors the person is wearing. And in the lowest part of it, of each of the 6 sections, you find a black ground truth. So here in this case, the ground truth is up here. Here the ground truth is here. Here the ground truth is here, here, and so on. Oops, here it is there and there. And what you can see here is already, with some examples, you can really find quite well with the sensors the activities, because the sensors are giving exactly the same signals as the ground truth. But with other activities, like the one in the first line and the one in the fourth line, you cannot see a clear indication of the activities a person is doing. And if you want to do it online, then even within a period of a couple of milliseconds, then you have to reduce it again, and in this case we could only detect about 12% of the activities the person performed. That means context detection is still a challenging task. So we have a lot of things which are really working reliable. That is the gesture interaction, that is the use of RFID tags. We develop within the project a lot of robust textile solutions which are acceptable. For example, a white code for interaction in the hospital, where you replace the interaction device with the user just with a conductive pad which is under the white code of the physician, and by movements along the white code, the physician is interacting with the system. We also develop things for indoor localization. I think the time is not enough to show you all these results. One thing we developed is that is a kind of a middleware which is required for the this is really hard for the system, for the variable computing system, and it consists of different blocks, building blocks for a variable computing solution. So one is for collaboration, because this is one of the requirements. Communication is another one, content management, giving people access to complex information. But for example, if we had complex 3D information like on the aircraft application, the devices were not able to work in a proper way so that the performance was satisfactory for the users. So there's still a lot of work necessary to improve the performance of these mobile devices and overcome this gap between energy and functionality. Context detection, localization as a special form of context detection, speech recognition, user interface, and workflow, that are the other parts we developed for this framework. So my conclusions, we have with variable computing systems developed for new user groups, but we are still at the very beginning. We have solutions which are working quite well for maintenance and assembly, but they use a lot of the sensory abilities of the users still. So the idea we had at the beginning of the project that sensors are available and it's no problem to do some sensor fusion and get out of the sensor signals the required information for an application, that was not possible. A field where we think a lot of potential is there, but it is a much longer way to come to real solutions, is emergency response, especially if we think of fire intervention. We found solutions for the Hetman scenario, which are quite interesting, and we think that in sports we have the driver for the technology for the future. We need systems which enable the dual task ability. So we believe that the focusing on mobile devices is a dead end because the mobile device will never support in an ambient way. So it could only be that the mobile device is supporting you in breaks between your primary tasks, but it is not able to perform you in an ambient way. We need much more to do on the sensors and on the context detection. Okay, thank you very much for your attention.
Thank you very much. We have time for some quick questions.
One question would be about the reception of your work and your solutions by the workers at the aircraft industry or in other places. I mean, at least looking at the video, I had a little bit the impression that this is like addressing yeah, low qualified people that can be replaced easily because they are steered by the system. I mean, me as a worker would object these type of things. Other experiences where highly qualified workers are really getting a grab in, well, new realms?
Yeah, so the example of the seat removal seems to be very simple, but in fact it is a very skilled work because, for example, the thing he did with the hammer and the screwdriver, that was a workaround. You need usually a special tool for that from aluminum alloy. You have to know that it is not working if you have a carpet in the plane. You have to know that you cannot use a steel screwdriver because then you destroy the aluminum alloy wheel. And that are things where we think, okay, this is pretty simple, but in fact it is not. And in reality, this work requires two workers because there is electricity involved and the mechanical thing. Besides this, we did a lot of experiments with more skilled things where we had to, where the people had to look into manuals quite often, and where the people had to do a lot of documentation work. And that is one of the big advantages of this technology. Documentation is done automatically, and that is why the people like it. Because otherwise they have to write it down, and there are people in the back office and they have to type it in. You have media breaks, as we call it. You have to change the media, and then you have the problem of failures. So what we found is that the people like it. However, if we really want to introduce it into such an organization like the car manufacturer, then you have also to see that it is a question of negotiation between the workers' union and all the stakeholders. So the stakeholders have all be involved to really make sure that the solution is accepted at the very end, and not only from the technical side, which is no doubt. The technical side is working if you take the restrictions I mentioned, but to accept it from the user's side, mean from all stakeholders, that is still a hurdle to be taken.
Thank you. So I personally would think that the variable computing would make your work more effective, and you can reduce the level of error you make during your work.
Yeah. So that are the two facts. So we can always say from the aircraft maintenance, we know that 50% of the time is just getting information and inputting information, and that increases the productivity by nearly 100% if you can really realize all of that. And the other thing is the avoidance of failure, of errors. We use this in the hospital environment where the physician is doing it at the patient's bed directly, all the medication, all the indications, and that was usually done, some notes by the nurse, and then in the back office they typed it in, and later on the physician signed it, and there were so many errors going along with that. And in the hospital in Steyr, they are now introducing this intelligent white code for all the departments. So that is something where you can say, okay, there is a solution for high-skilled workforce, because physicians, I think they are high-skilled, but the solution is hopefully, yeah. But the solution is quite simple, and it is completely variable, and yeah, so there's a nice outcome from the project. Yeah.
Okay, thank you very much. Thank you. So we have to move on. Our next presenter is Thomas Schmidt from Hamburg. I think there's no need for introduction. He's well known for the community. He was 2 years ago even the head of the program committee of the Terina conference, and will be speaking about a new video codec and its usage in mobility, mobile devices.
Yep. So, yep. Okay, may I steal the mic? Okay, good morning, everybody. So I'm glad to see so many faces on this prime slot after the big dinner. So what I want to introduce to you today is also an application area, but a much narrower one than the previous. This is a traditional application in networking, namely video conferencing, and shows this. Well, the reference to this old title when the movie was invented, because we are looking at mobile video conferencing. And this is a project, actually, this is part of a long ongoing collaboration we have. Did anybody attend Limerick, the TNC in Limerick here in the room? So you've been here. Maybe I've introduced this cooperation and this work in Limerick, and now I'm coming back to this. So this is joint work with a couple of people. Matthias, who is here, Gabriel, who is in my group in Hamburg, Hans Sykon is from another university in Berlin, and Mark Palko is from the company we are collaborating with. First, I want to introduce briefly the project and the objectives and the challenges. This project, MovieCast, is actually close to its end. It started 2.5 years ago. Then I tell you about this mobile video conferencing solution. That's actually a software solution that aims at being lightweight. And I just show you the components and its integration objectives with legacy MCUs and other stuff, and then the extensions for operating in a distributed fashion and facilitating session mobility. So MovieCast, the project was started about 2.5 years ago, and the idea was simple. We have a video conferencing system, and we want to, a software video conferencing system, and we wanted to extend this to mobiles, to handhelds, and that was the issue here. And well, we started from what I show you in a second, from quite an advanced software solution on the desktop, and try to extend this from the different aspects. And at the CeBIT 2008, that's more than a year ago, I guess we were the first to who could show an H.264 mobile video codec software on a smartphone. And lately, we also got this label right down. We won a prize for the IPv6 integration of video conferencing. What are the requirements? First of all, you have pretty rigid real-time requirements that mean that you have to do all the processing, all the transmission in real time on the mobile and also on the desktop, of course. What you want to have somehow, what you want to reach somehow is a scalable resource adaptive coding, and especially the encoding. The big thing is the encoding in video conferencing, as probably all of you know. The decoding is much less challenging. What we also looked at is mobility support on the network layer. I'm not talking about this today. We designed several solutions for group communication on the network layer, on the overlay. I'm also not talking specifically about this today. There are challenges in authentication. Especially if you are in a changing mobile regime, you are pretty much interested to authenticate the parties in your session, and to reliably authenticate the parties. Otherwise, you may have intruders disrupting, destroying your conference, and so on. Of course, what we try to do, and I guess we did, is we try to focus or stick to standard compliant solutions. And whenever we extended signaling and communication, we try to do it in a way that it is backward compatible and stays in the protocol frameworks we are using. So what is the starting point? The starting point is a desktop solution. That's a video conferencing system called nowadays PlaceCam. In the year 2002 in Limerick, it was still called the Davico conferencing system. And this is a software solution that can cope with something like a dozen video conference members on a regular machine, just on a standard machine. It is pure software. It has an H.264 codec with some SVC extensions, and this is the area where we work on in the moment. It has a peer-to-peer communication model. It is relatively simple communicate, to locate users. It has the support of IPv4, IPv6, zip, and unicast and multicast, and as we all know, multicast is a deployment issue, and it also has a large support to overcome NUTS, which is also a deployment issue, and we are not talking about this because it's boring. It's available for Windows and Linux. Yeah, we started from this and tried to work our way to different mobile use cases and showcases, and this is an early showcase. What we did is we actually implemented the codec, the encoder, on such a very small embedded system. This is put this on a train, and that was shown at the CeBIT 2007, I believe. And this so-called movie train could nicely demonstrate what this train does. There's a camera, and it drives around, and it captures the pictures, encodes them, and they are part of the conference up there. And it could nicely show how the complexity of the coding actually is at the edge. Whenever you drove the straight line, then the pictures are not changing so much. So actually the numerical capacity of the small embedded system could cope with the video coding. Whenever you turned on the ring, then the video pictures changed rapidly, and you could see the videos breaking in. This was just for fun. It attracted a lot of kids, and it was also fast to see the capabilities and demonstrate them. What we are more interested, or what we aim at, what we aimed at is real commodity hardware, and what we had to do is to take the codec and port it and optimize it for the mobile device, design a software stack for secure mobile group conferencing, and what we also target at, and we would speak about this a little bit, integrate all this into legacy device installations. Looking at the software stack, it looks a bit like this. You have the video processor, which is one of the key issues as a codec here, using the standard RTP part, and then the rest of the communication is particularly dedicated to zip and extensions we implemented in a standard compliant way, and we talk about this later. Let's first look at the codec. The starting point is this, we call it the DAF-C codec. That's an H.264 software encoder that has encoder decoder that is a baseline profile, follows a baseline profile, and the issues here is that it is particularly optimized for being real-time compliant. So it has those of you who are somehow involved with video codecs may know that the motion compensation is the big thing in calculating encoding, and it is particularly optimized to do this in a very efficient way, especially to early terminate the search for motion compensation strategies when it detects that there is no decent benefit of it. So that's what it does. It does a fast search in the spatial directions, and then pretty quickly decides whether it skips further search for motion compensation or it continues. What we did is we compared, and I'll show you values in a second. We compared our codec with the traditional open source implementation X264, which is also quite highly optimized, and also with the standard implementation. And here's a picture. Using the Aikido, that's one of the test sequences. Using the Aikido, you see the typical, that's signal to noise ratio, and this is the bit rate, and you see different curves. The lower one is a traditional MPEG-4. The most upper one is the reference implementation of the standard, and in between you see the DAF-C codec, this line, and the X264 codec. This is the lower line. And you see the difference between these lines is not only the quality of, or the ratio of quality to bandwidth, the efficiency of the codec, but also the real-time capabilities. So the DAF-C codec runs at a speed of 284 frames per second here. The X264 is similar, but for instance, the reference implementation is by no way real-time capable. Looking at a different sequence, you have a similar picture here. The DAF-C and the X264 are more similar, but still you have a gap in the real-time capabilities. So we ported this to the mobile, optimized this particularly for the X-Scale platform and for the Intel Atom. There is this prototype on Windows Mobile. We are still working on further optimizations, but what we achieved up till now is for like an average recent smartphone. This is a smartphone that's 1.5, 2 years old, so it's not the latest one. You can buy smartphones with about a gigahertz processor today. We can achieve something like an encoding of QSIF streams, 13 to 15 frames per second at a bandwidth requirement of 50 to 90 kilobit per second. If you compare this, for instance, like to commodity solutions, you may have seen their websites. You can use your handheld, you download some software on your handheld, and then you capture a video, and then you upload this to this website, and everybody can see where you've been. I don't know, you know these type of things. If you look at the codec they are using there, that's also software solutions. They reach about, they require capacity which is about 10 times higher. What they usually do is they do a differential upload. They do upload some of the pictures in real time and some later offline. What we can do is about 30 frames per second QSIF decoding, and if we do video conferencing, it's 5 to 10 frames, 5 frames per second encoding and 2 frames per second decoding in parallel and at the same time on the machine. And we are working in the moment on enhancements towards the direction of the SVC. And what we see as the main challenge here is if you add scalable video codec extensions to your codec, you usually add overhead. You add overhead from the complexity, from the numerical complexity, and you add overhead in terms of bandwidth or data. And what we are trying to do is to do this more or less without performance penalty. We're not through. We are in the middle of the work, but up until now we do this without performance penalty by applying further optimization. So the idea is make the codec scalable, but without making it less performant or less efficient. That's the comparison of the mobile codec to the full codec. What the mobile codec does is it reduces it works at a reduced complexity, and you see the gap is opening for higher bit rates or higher resolutions, but we are still pretty close to the quality picture at looking at a QSIF encoding of this Aikido sequence. Yeah, and that's probably a good moment to show you something. If I can use, does anybody ever was satisfied with an HP notebook? That's really, so I show, yeah, you see here, you see the PlayScam, and let's see how this works. So what I do is I take the member of the session we have here and try to call him. And let's see, we are seeing something. It's pretty dark here. So, what are you saying, Matthias? Can you use a mic, please? So we can do this a little bigger. So that's the,
how it works.
that's the native encoding coming from the video. It is not running, sorry?
Yeah, the audience has to show, to look on the Beamer presentation to see the effects on the video codec.
Yeah, maybe you can come up, then we can use this mic if the other doesn't work. The problem here is a little bit with the light. The light is low, and the camera of the mobile drops performance if the light is low. But maybe you can tell us what did you do? People saw what I did. What did you do?
Oh, what I do? I just wait on your call.
You started the software on the mobile phone?
Yeah, and the software connected to a register, which store my IP address and nothing else.
That was it.
Yeah.
And
Quite
what are we using here? What network?
IPv4, unfortunately.
And the IPv4 network is then just a regular wireless LAN.
Yeah, right.
Yeah. And so that's the system in life. Let's discuss a little bit. If I get along with this machine, that's really. Let's discuss a bit what we've done further. As I told you, it is important to integrate the system, and one of the integration tasks here is the integration into legacy MCUs, because people have legacy MCUs, and we are working with a commercial company, and the company wants to sell the stuff even to people who have a legacy MCU, and these legacy MCUs have the property that they somehow do speak a little bit zip, and they have some sort of special features offered by dial-tone multi-frequency, and they are especially working in a central way. So what we introduced is a so-called session border controller, is a session border controller that is taken in the Davico network as a blind client, and this redirects the media streams without transcoding and aggregates the zip session instructions, and does this in several ways. So what it does is it first of all delegates the zip conference control, but it also translates the control of the conference into these dial-tone multi-frequency stuff, which the MCUs like to have. That includes a fire and camera control for the MCUs, and that also includes the so-called fast update for iframes. That's an extension the MCUs use if they lose frames. You can request a new iframe. So what else did we do, Matthias?
We can integrate the different participants in IPv4 as well as IPv6 networks. The main problem is that in such transition phase, the devices can have different IP capabilities, so we need to be aware of this. What happens typically, you invite someone based on its email address, and this email address has to be resolved, so you contact a proxy server, but this proxy server may speak a different IP version as a caller with a callee, so we need a mechanism to mutually explore and decide on the protocol versions. The main problem is that ZIP, or the session description protocol itself, does not allow to negotiate several IP addresses, IP interfaces. So there's an extension for this, which is called alternate address type ANAT, but the problem is that the caller does not know if the callee is also aware of this extension. So what we are doing is that the caller sends just a pure zip invite session to the callee without the session description protocol, and based on this, the callee learns the minimal IP version of the caller and can then decide on its own which IP version it talks with the caller. And it can also let the decision to the caller if it sends a zip OK message to to the caller. And yeah, if we summarize these steps, the video conferencing client here sends, as I said, a pure invite to the MCU, and the MCU then establishes the STP handshake, and if the STP, afterwards the RTP session is established, and based on this, the video conferencing client can then control the MCU, and the MCU is also integrated in the IPv6 world based on the session border controller, which Thomas told you before. Using all this zip standard stuff, we can do some more fancy stuff. For example, to distribute the conference focus.
Yeah, that's not to give a wrong impression. We are not really, we are not focusing on MCUs. We are just trying to integrate them because they are there. Actually, we are heading at fully distributed conferencing. We just recently, 2 weeks ago, had a large test and could see an MCU breakdown, but Davik was still living. And what we actually want to have or to implement is, or to realize, is a fully distributed conference session where no central entity of the conference exists. And this has not been foreseen in the ZIP conferencing framework. As some of you may know, ZIP still, even in software and not like an MCU, requires to have a central conference focus. And what we did is we designed and implemented something that simulates a central conference focus, but actually is a distributed one. And we did this by transporting these ideas you may have heard yesterday in the IETF session into ZIP. But what we did is we did a split on the conference identifier and the conference locator. So actually using ZIP routing primitives, someone routes to the identifier but ends up by its nearest locator of the conference. So that's something which is not standard but can be done by standard means. So it is compatible. Yeah? It works together with other clients that are not aware of this mechanism, but still allows to establish a fully distributed ZIP conference that is then more scalable, error resilient, and all these things we have from distributed conferences. Well, and last but not least, with the issue of the session mobility, and this is what I give back to Matthias.
Yeah. The typical scenario could be that you are, for example, in a rush hour and you are too late for a meeting, which will happen somewhere. So you start your video conference on such a mobile, for example, and go to this meeting, and this meeting happens in such telepresence systems, and when you arrive, you want to transfer your session from your mobile to such a telepresence device, and you want to do this without any interruptions. So what you have to do, you have preserve your zip session, as some properties, for example, are associated with this session, and this means that you cannot initiate a regular zip invite. But what we are doing is that the caller, the conference participant, first requests potential devices from the location server, and the location server replies with the potential devices, and afterwards the conference participant decides for one, and in this case it is Charlie at home, so it sends a refer message to Charlie so that this device can send a re-invite to all other group members, and yeah, and whoops, what's that? And after the re-invite has finished, the session description will also be renegotiated to rescale these small pictures to a full screen. Okay. So, and to conclude.
Yeah, sum up. We are finished. I already got the signal. So what we did is we tried to work out a mobile video conferencing solution, or extend a static video conferencing solution into the mobile regime, and try to do this, and that's stressed here, try to do this with as high quality aspects as possible, because we like to, I mean, we all like to have high quality video. We don't like the low quality type of thing, and actually what we see as limitations here is the cameras of the mobile devices that are not as good as the big Sony you see at video there or somewhere. What we also looked at is to extend the ZIP framework in a standard compliant way, to give it more capabilities, distribute, for instance, group conferencing, and better support mobility and user sessions. And in the future, we will look at more closely at the SVC encoding, of course. And we also, maybe we have a student who is really good in this, and we try to bring this conferencing extensions into the IETF where there is room more on these type of things. So, contact details. Thank you very much for listening. The partners are Davico, the Fachhochschule für Technik und Wirtschaft. It's now called HTW. The HAW are real. LinkLab is and Fraunhofer Focus are, well, LinkLab is a company. Fraunhofer Focus is a research institute, a well-known one. Those are contact details. This is the company. And I also would like to advertise a book that describes our conferencing, in the chapter, our conferencing extensions, and this is our team. Is that right? Yeah. You sure? You know who the guy in the middle is? In the middle? Yeah? No. You don't recognize him? That is Khan, Rob Khan. Rob's Khan.
Okay. Thank you very much. Quick questions? Okay, then thank you very much. Just a very short advertisement. In the cyber cafe in the room right over there, we have the American company called Video, and they have a very nice demonstration of the H.264 video codec. So I would suggest you to go there. Because they can give you very detailed information about the codec, and they can also demonstrate the power of HD with this technology. So, okay, so let me introduce our next speaker, Thomas Weisflecker from the University of Graz from Austria. He's a young researcher, and his main topic is indoor navigation without having GPS, VLAN access points, and RFID technology due to demanding environmental conditions. Thomas? Thank you.
So thank you very much for this introduction. My name is Thomas Wiesflecker. I come from Graz University of Technology, which is located in Austria. My journey here to Malaga is funded by Acconet. Thank you very much. It's my pleasure to have you here in the auditorium. I welcome you to my presentation. I'm afraid I'm not that into networking today. I will rather give you a presentation about one more valuable application of networking technologies. Nevertheless, I will try to give you an interesting presentation. The title of my presentation is A Distributed Indoor Navigation System Leaving the Trails. Let's start with the current situation in cities. According to the United Nations organization, more than 50% of the world's population is located in cities nowadays. So we have to face very complex and large real estates. Everyday life takes place in these large real estates. There are many disadvantages very closely linked to this development. For example, we must be able to evacuate these large real estates within a very short period of time. What might happen if we are not able to do so, you can see in the figure on the right-hand side. This picture shows you the outcome of a terrorist attack against the subway system in Tokyo a couple of years ago. So there's the very strong demand, there's the desperate demand for effective disaster management, especially for the built, for the roofed environment. Why do we need indoor positioning? It is very difficult to overview and to access these large real estates in the event of an extraordinary event. Here I'm addressing a natural hazard or an industrial incident, for example. It would be very beneficial if we would have all the current positions of all the people staying within these real estates, or at least of the rescue teams deployed in these buildings. So by providing the means for indoor positioning, we can increase building security, we can alleviate disaster management, and we can mitigate the consequences of extraordinary events. There are some more advantages of indoor positioning more closely related to the civil usage. We can save time and costs, for example, and we can increase end-user satisfaction. All of us know the situations when we are looking for a certain office in a foreign building, or if you want to have prompt access to a store offering us some categories of products, so it could be very beneficial to have indoor navigation. It's the same like for GPS outdoors. I would like to give you a very short overview of existing positioning technologies in this presentation. Afterwards, I would like to introduce you to a new system currently being developed at Graz University of Technology, offering indoor positioning functionalities. This system is called Computer-Aided Disaster Management System, CADAMS. I would like to focus on indoor map matching because this is the core part, the core component of our system, and then I will conclude with some short qualitative evaluations of the system. So why do we need to leave the trail? Why do we need one more positioning system? As we all know, we have GPS. It works nearly perfect outside, outdoors. But as you all know, GPS cannot be deployed inside buildings. Due to the concrete and to the steel which our buildings are made of, we have to face attenuation, deep outages and so on, so we can't use GPS inside building, especially deep inside the building or especially on subsurface floors. Second, there are some positioning technologies dedicated to the usage inside buildings. For example, RFID, Wi-Fi positions based on time of arrival systems, UWB fingerprint systems and so on. But, and this is the main disadvantage of these systems, they all depend on stationary infrastructure installed in the building. So this approach is hardly adaptive, it's cost intensive, and more aggravating, it is not suitable during an incident, because all this fixed infrastructure in the building can cease working in the event of an industrial incident, for example. It could be due to a simple power outage. And a third reason why we can't use existing positioning technologies indoors, current map matching technologies are dedicated to road networks, to road traffic, and can't be deployed inside buildings. I will give you more details concerning this point later on. So our conclusion is that we have to develop a completely new indoor positioning system, and this is done at Graz University of Technology. the main benefit of our system, of our computer-aided disaster management system, is that it is able to work completely autonomously. It does not rely on any fixed infrastructure in the building. Here we have a very short overview of the main components, of the main modules of our indoor positioning system. We are collecting acceleration data with inertial measurement units. We provide a sophisticated graphical user interface, so we provide a digital floor plan and the current position of pedestrians in these floor plans. We transmit this current position of the people staying in the building to the other clients, to the other service customers. At this point, you could say, well, fine, let's sell this project, let's offer indoor positioning. Unfortunately, it is not that easy. This is due to the fact that collected acceleration data are very imprecise, they are very inaccurate. So we have to introduce some mechanisms that automatically correct these scattered acceleration data. We conduct this by the means of a building information model and by the means of indoor map matching. Let's have a look at the deployed hardware. On the left, you can see two types of inertial measurement units, IMUs. Currently, they are getting smaller. These inertial measurement units gather acceleration data in 3 dimensions, and they gather the current angle of the pedestrian's trajectory as well. These data are updated with a frequency of 50 Hertz. Especially for the case of emergency, we have our graphical user interface on head-mounted displays, like you can see it on the figure on the right-hand side. These head-mounted displays can be mounted easily on helmets, for example. And in the middle, this is not shown here on this slide, we have a mobile device, like a smartphone, that brings these two hardware devices together and that performs the analysis. It is our prospect to bring all these devices together into a smartphone, for example. Newer versions of smartphone include some kind of acceleration measurements, of acceleration sensors. Here's a very brief overview of the main system architecture. We have 2 main sources of data in our system. In the upper block, called CAFM, Computer-Aided Facility Management, here on this slide, you can see the static data we are using for our system. These static data contain of information describing the building. We import these static data from computer-aided design applications. On the bottom, you can see the real-time data, the dynamic data. This is related to locally gathered IMU data, acceleration data, and we have wireless network access. We can transmit our current position, which is generated locally here at the system, to other users, to other clients. In the middle, in the center of the slide, you can see the update engine. This is a part of software. It brings all the measurements together and performs some calculations. The outcome is the current position of a pedestrian inside a building. This is depicted on the right-hand side in red characters. I don't want to bore you with the requirements of the building information model. I just want to comment that we are not only relying on graphical data, on graphical primitives on the floor plans, but we have also some information on the rooms. For example, we have the number of the room, the title of the room, we have the main usage of the room, all the kinds of information that could be interesting for the pedestrians. Furthermore, we have room polygons, we have knowledge about the structure, the logical structure of the building, and so on. Just keep in mind that this building information model is prepared for conducting indoor positioning and for being exploited for indoor positioning. Here you can see the structure, the logical structure of this building information model. It represents the building, the real estates, logically by the means of computer science. So you can go from the real estate containing several buildings down to some other entities like rooms and area objects. I don't want to refer to this in greater detail. This is the main data structure we use for our computer-aided disaster management system. So, as you might have figured out, it is not sufficient to only have access to such a billing information model. It has to be exploited in some way to correct the physically gathered inertial measurement data. To understand how this is conducted, we must have a very short look at map matching like it is done for the road network, for GPS navigation, for example. On the first figure, you can see a picture of a road network. You have a motorway, a highway, which a car is driving on. This you can see on the first figure. In the second figure, on the bottom, you can see the digital representation of this road network. It is represented by a mathematical graph, as you can see. The vertices represent the road crossings, and the edges represent the streets connecting these road crossings. This way of digital representation is sufficient. It is proved to be sufficient because most of us use GPS, and most of the times, not always, but most of the times, we have been guided correctly. So this approach to digitally representing a road network is sufficient for road traffic. But in our billing information model, we don't have such a mathematical graph. We have a more sophisticated representation of the building. We can't represent it by only using line segments. And this is the reason why we can't use conventional map matching technologies for indoor positioning. How is indoor positioning, how is indoor map matching conducted within our system? We have two main categories of repositioning, of recorrecting the physically gathered inertial measurements data. We have automatic repositioning. This is conducted like in GPS navigation, so it is done without user interaction. The user might not even notice that the physically measured positions are corrected. And as a second choice, if we can't guarantee the exact position, we have some kind of user interaction, we have some kind of manual repositioning. But this is only the second choice if it is not sufficient to use automatic repositioning. Here we have the main data flow in our system. This flow has to be conducted for each physical determined position. The main block here on the left-hand side with red capitals is the plausibility check and the automatic repositioning. I don't want to concern you with this very complicated graph. Here I've broken down this very compact block from the previous slide. So you can see when conducting indoor positioning, the situation can become very complex or even complicated. We have to compute many decisions. For example, we have to figure out if the physically measured position is inside the building or if it is outside the building. We have to figure out if the user's trajectory intersects a wall or if it intersects a door or if it is close to a stair and so on. So it might get very complicated. This is only a very general overview of the data flow. I like this slide much more because it is much more easily understandable. It points out the main idea of our approach to indoor positioning. You have here a floor plan presenting 3 rooms. You have a user. He is changing the rooms. He comes from the left-hand side and walks to the right. He's entering the large room on the right-hand side. Unfortunately, his trajectory measured by these IMUs is intersecting the wall, as you can figure out here on the slide. Fortunately, this intersecting point is close to a door. We can exploit the knowledge that we are here close to a door, and we can move the position points, the indicator shown to the user, more close to the door. So we can adapt the presented position in a way that it is more plausible. Of course, this can be described by more sophisticated means of mathematics and geometry. On this slide here, you have the geometric explanation of the problem. We have many types of correction. We do not only exploit the knowledge on doors, we also exploit the knowledge on stairs. For example, here we have the result of such a stair correction. if the physically determined measurement data are not touching the stair, for example, as it is shown here, even though the user is entering the staircase and is walking up the stair, we can exploit, for example, the height coordinate, and we can exploit the knowledge that we are in the surrounding of a stair, and so we can adapt the position in a way that it is pulled towards the stair. It is shown like here. So the position points displayed to the user offer some kind of jump discontinuity here. But this is much better than showing physically impossible positions. This is only a very general example of a stair correction without any mathematical background. Just to give you an impression how manual repositioning could work, I will describe the first figure here on this slide. If the user is approaching two doors which are very closely together, the user can select which door he will traverse. So he can convey a message to the system that he will traverse door 1, for example. This can be conducted by speech recognition. But I mention it once again, this is only the second choice if the means of automatic repositioning are not sufficient. Let's come to a brief qualitative evaluation of our system. I'm in lack of a laser pointer, so I can't show you the exact path a user took here through the building. You can see a floor plan of a very complicated building, and we tracked the path of a user who took a walk through this building. The red circles here, oh, thank you. Thanks. The user walked here through this corridor. He approached the staircase and he walked up the two stairs. Then he returned on almost the same route on the upper floor towards his starting points. He entered this staircase and he approached his starting point on the lower floor. Here you can see the measurement results. They are based purely on the integration of accelerations and of the analysis of the angles. As you can see, the uncorrected measurement results are very imprecise, they are very inaccurate. In fact, they cannot be used for indoor positioning. Here you have a deviation of a couple of meters, for example. Here you are intersecting a wall, you are entering rooms that the user didn't enter and so on. So this result, this uncorrected data are not usable for indoor positioning. But since we have implemented intelligent algorithms for indoor map matching, we can correct this data automatically. Here you can see that the trajectory is pulled back to the stair because we can exploit the knowledge of the height coordinate. The same thing is here conducted for the second stair. Then we can track the user's path on the upper floor. And as you can see, all these distortions, all these deviations can be, at least in this qualitative example, can be corrected by this means of automatic indoor positioning, indoor navigation. Let's come to a second qualitative example. Now we have changed the physical sensoring subsystem. We are using here another type of inertial measurement unit, and now this IMU is mounted on the pedestrian's foot. In the previous example, the IMU was mounted on the upper body, for example. On the left-hand side, again, you can see the pure measurement results, the uncorrected measurement results. Here you can see other types of distortion. The curve looks to be a little bit more smooth. It looks more smoother, but it is as inaccurate as in the example before. You can't use it for indoor positioning. On the right-hand side, you see the same data, but with indoor map matching deployed. And as you can see, these seem to be quite good results. Most of the deviations are corrected here, and the positions shown to the user find back to the starting point. I have a third and last example here on my slide. We are using the same measuring subsystem here, but we have changed the geometry, the building geometry. So we are assessing here in another building. On the left-hand side, again, you see the uncorrected data. We are, again, intersecting walls, entering rooms incorrectly, and so on. And on the right-hand side, you see the automatically corrected data. And as you can figure out, this trajectory shown to the user seems to be quite reasonable. The results seem to be quite reasonable. So these are only 3 qualitative results. These are not based on statistical means. Let's come to the conclusions. What have we done here in this project? The measurement results reveal that the developed approach to providing seamless autonomous indoor positioning can function in practice. This is the point that we wanted to figure out. We wanted to try out if seamless autonomous indoor positioning is possible in practice. We have shown this by using different sensoring subsystems and by using different building geometries. The combination of static building information model data and dynamically generated sensor data improves the accuracy of indoor positioning significantly. There seems to be a trade-off between comprehensive building modeling and improved indoor positioning accuracy. So as it applies for most of the projects, there is some future work to do. There's still a long way to go. In the next couple of months, we want to refine our algorithms, and we further want to improve positioning accuracy. And for example, in the summer, there will some tests during regular fire practice, and there will also be some serialized, standardized test series. Okay, I think I'm already through. Thank you for your attention. I'm looking forward to receiving your comprehensive questions. Thank you.
Thank you very much. Seems like an absolutely usable application in real-world environment.
Yeah.
One question, how does your work relate to pedestrian dead reckoning? To pedestrian dead reckoning. So in literature, this procedure is known, and the second question is, if you mount your IMU on the foot, do you use a velocity update for the Z coordinate?
Yeah. The first question referred to dead reckoning. Yes, we are very closely related to dead reckoning. We are using inertial measurement units. These conduct dead reckoning like it is done by beds, for example. Yes, we use dead reckoning. It is the same, yes. It relies on dead reckoning, yes. Yes, our approach relies on dead reckoning, yeah. On inertial measuring, on dead reckoning, yes. The second question referred to the evaluation of the height coordinate. We measure the accelerations by the inertial measurement units. Then we conduct a double integration over time, and this yields a distance. And this is done also for the Z coordinate.
Foot on the ground,
yeah?
Then you have a kind of a ground truth, and this ground truth means that the velocity has to be 0.
Yes, yeah.
And that means that the quality of your data is much better than if you put it, for example, as a hip.
Yes, you're very correct. Yes, exactly. Yeah, we can, just a few technical details, we can restart the integration when the velocity equals 0, yes. So it's much more difficult if the sensor is mounted on your upper body, for example. But for civil usage, it's much more valuable, of course. Yeah.
Can you tell us something, let's say an indicative price of this technology? So how expensive it is?
At the moment, it's quite expensive. We had to import those IMUs from the US. The price for one of these IMUs is at the moment approximately $2,000. At the moment, yes, we hope that it will become less, but it seems to be that most of the modern smartphones have acceleration sensors integrated. So this is our prospect. We want to use normal, conventional smartphones. They will have some kind of acceleration sensors built in the future. But at the moment, it's yeah, quite expensive.
The examples you showed us on the trails were all with very well-defined narrow paths. Have you made experiments on less well-defined environments like shopping centers, airports, where people can walk like kilometers without correcting walls?
Yes, it's getting more difficult. Yes, it's more beneficial for us, it's more advantageous for us if you have those small corridors or those doors, because then we can conduct this automatic repositioning. If you have a large hall, for example, without any reference point where we can reposition, it's getting more difficult, yes,
Yeah.
because you have drift.
Do you have a number? Like, is the error more than, is it close to 100%? Is it close to 1,000%? Or
the drift, the deviation of the IMUs is very large. If you mount an IMU on a table, for example, and you leave it untouched for an hour, the measurement results can drift a few thousand meters, for example. Only if the IMU is put on the table and not touched for 1 hour. So the drift is very big, unfortunately. Yes.
So we did in the Variety at Work project also some experiments with this technology, and we use it also in large halls and in buildings where we assumed that there was a destruction, so that we could not rely on a plan. And we got accuracy for repeated passes of about 4 meters if you have a distance of 1 kilometer.
Okay, yeah, this seems to be quite reasonable. Yeah, here we have a deviation of, let's have a look at this slide. Yeah, here you have a deviation of a few meters, for example. After approximately 1 minute, 1.5 minutes of walking through the building, so you have a few meters of deviation here, of distortion here, without conducting indoor map matching. Yeah. Yes, yeah, that's correct. Yeah, it's on a it's on a lower layer here. Yes, yeah. Only integrating over time is not enough. Yes.
Any more questions? Okay, thank you, Thomas. It was really interesting.
Hopefully, thanks.
And have good luck for future research.
Thank you. I hope we will not get lost.
Okay, so this is the end of the parallel sessions. Thank you very much for participation. We have a short lunch and meet you at the closing plenary session and next year's conference. Hope you enjoyed. Thank you very much.